All right, we're going to continue our discussion of Riemann normal coordinates here. We left off last time having derived this from the basic axioms of general relativity. And what we basically learned is that we can find these two matrices which will diagonalize the metric, right? Diagonalizing meaning delivering to us a Minkowski Cartesian metric. And this can be done using just the basic ideas of the Einstein Equivalence Principle, the assumption that spacetime is a manifold, and we walked ourselves right into this expression. And we also, as on our way to that expression, we had expanded the coordinate transformations, right? The coordinate transformations E, A of x and x alpha of, I keep calling it E, but it's psi, right? It's xi, I guess. And we know these two coordinate transformations, they're inverses of each other, and we can certainly express them as a Taylor series because we have a differentiable manifold. So these functions are known, and if those functions are known, so are these derivatives. And what's important is once this is established, we can think of this as an equation for these transformations. These transformations are fixed by this relationship. Now, they're not necessarily unique. And eventually we'll talk about how unique they are, but they definitely exist. And they are, once they're chosen, this fixes them. And so what this basically tells us is that this condition given to us by the axioms of general relativity fixes this coordinate transformation up to first order, right? Because these guys here are actually these guys here by definition, right? In other words, E alpha A is defined as partial psi A, well, it's the other way around, right? E A alpha is partial psi A partial x alpha. And the way they're expressed here is as their inverses because we have E A alpha times E alpha A is delta not delta, what am I saying? Not delta, delta A alpha, right? So this is just the inverse, right? This guy here is the inverse, but this fixes that. So it establishes this whole formula to first order. Wait a minute, what's wrong here? No, you know what this has to be? This has to be E alpha, this has to be a B, right? B, and then this is delta, not alpha. This is crazy. Why did you guys let me do this? See, if this was a real classroom, you would have shouted me down, right? There it is. I'm sure there's probably things that I've already let slip. In the comments, people constantly tell me things that I would never have gotten away with in a real lecture with people, right? All right, so now we have a look at the second order term. The second order term is of interest to us. And to tease it apart, we are going to introduce and remind ourselves about how the Christoffel symbols change under a transformation. So I clipped this out from a text that I like a lot, and we're going to have a look at this. So this is the transformation expression between two coordinate systems for the Christoffel symbol. Now you'll notice here, this guy uses the gap, right? This guy uses the gap notation. So be it. It's not important. This is still the relationship that we're interested in. But now what we have, so we just got to get used to doing this, right? Our system is transforming from, say, the inertial system, which would be C, right? So this is C1 through Cn. Now, of course, for our case, n equals 4, right? It's a four-dimensional system. And then this one is just x. So this is x mu over here, and this is c mu over here. So where I'm going to translate this formula into the formula that we can use for our own work. And we have a slightly different, we would write NP like this. And so, but this is a sort of a trivial convention that doesn't really matter so much. But we got to make sure we set it up to going in the right direction. So we're going from our system that's inertial at the point P, because it's not really an inertial coordinate system, it's inertial at the point P, and to some arbitrary system. So how would we write this? And the way we would write it, I think, is like this. It would, well, first of all, we'll take this and we'll change it to ABC, right, instead of MNP, and we'll use our convention. And then these coordinates being the inertial at P coordinates to the arbitrary coordinates would mean the let's see. So this is inertial at P. This is inertial at P. So that's C and C. So I did those first. Summing over B, summing over the lower index N, summing over C, summing over the lower index P. And then this guy goes the other way because you're transforming the upper index. Now, this looks exactly like a tensor, right? Exactly like a tensor expression. But this whole transformation is obviously not a tensor expression because you have this part right here. So I want to talk about that for a moment, but let me just write down the non-tensor part, which I'll put in red. This is going to be the second derivative of the inertial at P coordinates, which I'll just use the same indices that they used in the formula, M, and then partial xk, partial xl, and then it's partial xi, partial xm. And this better sum up to something with just, it has to have three indices. So these are dummy indices, and this index is up, and then there's two down indices, and that matches what we're after. So this whole thing is how you would transform any connection in this differential topology. And we studied this. We learned how this worked in the earliest part of these lectures. And again, you can walk this through with using the Einstein Equivalence Principle and other things. This is just how connections transform if you transform a coordinate system. Now we're going to use this. We're going to use this fact to figure out what this guy is here, this second order term. And you'll notice it's got one up and two down indices, just like this does. So it shouldn't be a surprise that this is going to be related to the connection. And the metric, this rule was sort of fixed by the Einstein Equivalence Principle, right? Telling us that we could always get into Minkowski spacetime at any point. And then the geodesic equation let us know that the connection itself would be zero at that same point. So that's the second fact we're going to use, and that second fact is what's going to fix this term. And so the assumptions of general relativity are going to tell us what the transformation between an arbitrary coordinate system and a inertial at P system to second order. It's going to fix it all the way up to second order. A quick note before we move on. This part is the tensor transformation part, meaning if this guy was a tensor, this is exactly how a tensor would transform. And boy, did we spend a lot of time talking about that in the What is a Tensor series. I explained exactly why this is a tensor transformation. But a good question would be like, why does everything have to be a tensor? Why is it so important that in physics we always have to have tensor transformations? And so, or why does all the things in our equations have to be tensors as opposed to something else? Why can't something transform this way? What's the problem? And this is a good chance to just sort of call out one way of thinking about the problem. Imagine that this was a physical quantity expressed in some coordinate system, I guess in the psi coordinate system. And this is the same physical quantity expressed in the x coordinate system. Now we know the components are going to change, right? That's true for tensors and non-tensors alike. The components of these objects are going to change. But here's the big deal. If this was a physical quantity right here, say it was a physical quantity that represented, say, mass or energy or something. And I just multiplied it arbitrarily by 2, right? I said I'm going to double down on the energy or the mass or the speed or something, some physical phenomenon that, I'm going to double it, number of particles, whatever is being represented by this physical quantity, I'm doubling it, just a factor of 2. Well, if this was all that was left, all that was relevant to the transformation, right? This is a linear transformation, right? That's its whole shtick, is that it's linear. So if I put a 2 here, when I transform it, I'm going to end up with a 2 here, right? I'm going to double it in every reference frame. And that's going to be completely independent of the coordinate. I could have these could be arbitrary numbers, but if I double this physical quantity here and keep these arbitrary coordinates the same, I double this here overall. If I were to change the coordinate transformation to some other coordinate transformation, and I still doubled this, I would still come out with something that was doubled on the other side. But if you have this kind of thing, right, I double this, right, then this doesn't really double. Part of it doubles, but then the other part is all dependent on the coordinates I'm choosing, right? And suddenly, doubling a physical thing in one reference frame doesn't translate to doubling it in another reference frame. Ergo, this physical phenomenon is coordinate dependent, meaning I choose the coordinates, I'm actually choosing how this physical object looks or is, not just how it looks, but what it really is, its size. It's not 2 times the original version, it's 2 times plus something that depends on the coordinates. Because you'll notice, this gamma is not here in the coordinates. So that's the key. That's why everything has to be a linear tensor transformation, is because physical things should never, ever matter on what the coordinate is. So all this junk that hangs out at the end, we can't have that. But this guy is not a tensor. It's a geometric quantity. It's not a physical quantity. It is a geometric quantity. So it can actually tell you a lot about how the coordinate system operates. It's allowed to have those kinds of components to it. Doubling the connection in one frame does not need to translate to doubling it in another frame. It just has to be the right match. And in this case, the right match is not a tensorial linear match. It's a match that has a tensor type piece plus a piece that's really very sensitive to the specific coordinate transformation you're going to make. Because remember, all of this ends up depending on the equations E mu of x and x mu of psi mu of x and x mu of psi. Okay, so there's a little diversion into why the physics of GR has to be tensor transformations. Okay, so now back to this actual transformation and how are we going to exploit it? Oops, look, this is wrong, right? This is not correct. Right here, that should be a psi m, right? Okay. So the first thing we're going to do is we're going to rewrite this expression a little bit. What I'm going to do is I'm going to multiply both sides by the inverse of this matrix here, right? So I'm going to end up with a matrix over here. Oops, another little, see, I'm copying a little too literally here, or I'm not, or this needs to be an A, right? Because this has to end up being that, and you need a B and C down here, so this and this need to be B and C, right? So this needs to be XB and XC like that, right? See, what I did was I took literally from this expression, right? I literally copied these indices, and they're, this has an upper I, so you ended up with an upper I here, but we have an A here, so this A ends up becoming an alpha through this transformation, and you end up with an A here, and that M is a dummy index, and you have B and C down here. So where's my This is B and C here. So those are B and C. So this ends, you need an alpha and beta at the bottom. Hold on. Let me get this right. This has got to be beta, and this has got to be gamma and M, and this A, of course, these are all Greek letters, right? So why do I have an A there? You have to have an alpha there. Okay, so that's going to work, right? So you have the summing over B, the summing over C, leaving beta and gamma, the summing over, this converts that to beta and gamma, then alpha is summing over A, leaves alpha, and then the same thing here, this sums over M, you have alpha, beta, gamma. Okay, fine, so this is correct. So now I'm going to multiply by the inverse of this, right? Because you see this, here's what I should do is these two M's here, these are dummy indices. First thing I'll do is I'll change them, because I can change dummy indices all I want, and I'm going to change them to A and A, right? So now I can take the inverse of partial x alpha partial psi A, partial x alpha partial psi A, and I can multiply both sides by the inverse of this matrix, which we're just taking to be the reciprocal of the transformation. So I can write partial, let me do this in... All right, so now these guys, we've actually, speaking of those things, we know that this is going to be given by E. We've already kind of established what this is. This is E B beta. This would be E C gamma, right? And this, in the previous lecture, we just gave this a name. We called it FA beta gamma, right? We just took this whole thing and we gave it this sort of compact name. So we can rewrite this expression a little more tightly. This is E A alpha. So we can rewrite the blue expression more tightly as such, right? And these were fixed by this principle here, right? This part of the Einstein Equivalence Principle fixes these guys. Doesn't make they're unique, by the way, but it does fix them. And, or once chosen, they're unambiguous. And so that's good. This is unknown to us, right? We don't know what that is. And when I say we don't know what this is, what I mean is we look at the second order Taylor expansion. We know what this guy is. We know the coordinates. It's sort of an initial condition. Like we could set this to 0. We could say that in our new coordinate system, we want the coordinates of x at the point P to be 0, right? So that's easy. This is, as I've been saying before, fixed by the Einstein Equivalence Principle. And this is not known yet. We understand what the first derivatives of the transformation expressions have to be. We know what those have to be because those have to be whatever it takes to diagonalize the metric. These guys have to be chosen in order to satisfy the second part of the Einstein Equivalence Principle, that the connection should be 0 at the point P. And so we know that the connection is going to be 0 at this inertial at P system. So we know this term is 0. And all of this, ergo, goes away, leaving us with just the following. And this expression, we have to understand, of course, that this is at P. This was at the point P. And that's why we can cross this off, right? Because we know that the connection in the psi coordinate system, which is what this is, at psi of P, right, equals 0. And that's, again, by the Einstein Equivalence Principle, right? The Einstein Equivalence Principle. So given that, we now know what these guys are, right? These guys in so why is that important? Well, we go back here and we say, well, we need those guys to understand what's the second order term. What's the second order term of the transformation, right? We're sort of seeking this formula for the transformation from the arbitrary coordinate system to the inertial at P system, and we fixed the 0th order, the first order term, and now we've fixed this term. And the reason we fixed this term is because we know we have our coordinate system in X. You may remember this is a picture from the last lesson. Our coordinate system at X, we know what the metric is in that system, and we know what the connection is in that system. So if we know the connection at that system, then we certainly know what the value of the connection is at P. We know the value of the metric at P, right? So when we land here and we're trying to find out what's the second order term to transform from some inertial at P system to this arbitrary X, well, what do I need? I need the known connection at P and then this matrix, this E matrix, which was already fixed by our first invocation of the Einstein Equivalence Principle that asserted that the metric has to be diagonal. So this is entirely known, is my point. This was the unknown, and now I can substitute it back into this expression. And let's do that. Let's clean up this expression using what we now know about this and about this. Okay, so I've written it twice. We're going to take this one first, and I just, in the second version of it, going to erase it, and I'll put in E, A, eta. And then in this second part, I will take this and erase this and put in, I'm going to put in this guy, E A alpha, gamma alpha, beta gamma. So it's E A alpha, gamma alpha, beta gamma. Now does that work? Let's see, the beta's sum, the gamma's sum, the alpha's sum, you're left with an alpha, you're left with an A, which is an A. So now we've nailed down the transformation expression to second order. So understand what this is now telling us. To second order, we understand how to take the coordinates of an arbitrary coordinate system, right, and to transform to a new coordinate system that is inertial at P. And we know how to do this because we can solve for this guy using the Einstein Equivalence Principle and this expression, right? We diagonalize the metric, right? That's another way. It's just a fancy way of saying diagonalize the metric, right? Where diagonal means minus 1, 1, 1, 1 on the diagonal. And then we take the known connection in the arbitrary system and this diagonalizing matrix, and we run it through this part. And now we know the transformation from the arbitrary coordinates to these new cool inertial coordinates up to second order. All right? Now there's all these higher order terms here, right? Higher order terms, and they have their own versions of this, right? There's going to be another x minus x, p, alpha, beta, gamma, say delta, and then there's going to be yet an additional. It's going to be d, cubed, e, a, partial. Let's see. I guess it would be partial x beta, partial x gamma, partial x delta, like that, right? And it's going to be, we'll have to call that HA beta gamma delta with 3 subscripts, right? But we're not going to go that far. We've really run out of conditions, right? We've run out of, the Einstein Equivalence Principle doesn't go on forever, right? We can't make all of these terms fixed. We definitely can fix to second order this transformation, but these higher order terms, we can't fix those. So this transformation, it's known pretty well, But it's not absolutely unique because these higher order terms can still be played around with. Okay, so with that in mind, now it's time to sort of make contact with the material we did previously regarding all of those geodesics, right? Remember those geodesics emanating from a point P. So we can actually just do that again. We have our point P, and we know the geodesic equation, which I'm going to write as x double dot alpha plus gamma alpha beta gamma x dot beta x dot gamma equals 0. And remember, the dot, right, these dots here mean d by ds, where s is the parameter. In fact, I'm going to go back to tau here because the notes that I'm using to produce this have a tau here. So this will be d by d tau, where tau is the parameter of the curve. But again, remember, don't let this trigger you onto getting purely time-like curves. This is just the parameter for the geodesic line. Okay, so we can consider now geodesics emanating from this point, right? Geodesics that go through this point and flow through space-time, but go through that point. And of course, there's an infinite number of them. But what does it take for us to get a hold of any given geodesic? Well, there's two critical things. First, the first thing we need is, oh, by the way, this is an arbitrary coordinate system, right? We're back into an arbitrary coordinate system. What I'm going to do is I'm reconstructing this geodesic emanation argument that we talked about in a previous lesson, and we're going to make contact with this inertial coordinates at P argument, all right? So we're kind of starting fresh, and we're going to come back and connect to this. So we have this arbitrary coordinate system. The geodesics, of course, are now given by x alpha of tau, right? X alpha of tau. And each one of these is a geodesic. Well, how do I fix it, right? How do I make the solutions of this unique, right? And the only way to make a solution unique is to establish initial conditions. So I'm going to set this so x alpha when tau equals 0 to be the coordinates of P. So that's going to be x alpha of P, right? So this is the coordinates of the point P, and this is the geodesic itself. You know, I'm feeling like naming the coordinates and naming the geodesic path it's done frequently in general relativity books, but I'm very tempted to change that right on the fly here. We'll just leave it as it is. Understand that this represents the geodesic path. This is the coordinates of the point P in the x coordinate system, right? And then, but the other thing you need is that at the point P, you need to know x dot alpha at 0, right? You need to know the tangent vector. So if I know a point in space where the geodesic goes through, and I know the tangent vector of the geodesic at that point in space, this unambiguously and absolutely selects all the points along the geodesic, right? And the tangent vector and that point will absolutely fix this. And we saw in the previous lecture that if I double the length of the tangent vector, the geodesic doesn't change. It's just the rate that the parameter goes through the geodesic changes. You're changing sort of the units of time if this was considered to be a proper time. And so, you know, that's the only thing that changes is how quickly you move along the geodesic. Given a change in the parameter, how much change do you have in the geodesic? But the geodesic points itself is the same as long as this tangent vector is going in the same direction. And that's what this is. This is the tangent vector. So we're going to set that to be the initial vector. We'll call it V alpha at P, right? V alpha at P. That's the initial vector. So these are the initial conditions that solve this geodesic equation. And for these two particular initial conditions, you're going to get this particular geodesic. And all the geodesics share this initial condition because they all go through the point P. but this is the one that distinguishes each and every other geodesic that goes through the point P. All right, that should sound awfully familiar from the previous lecture, right? But with this, I can now write down the geodesic equation again, x double dot alpha at tau equals 0 equals opposite alpha, beta, gamma. Then this would have to be v beta at P and v gamma at P, right? This is now an expression of the geodesic equation by applying this initial condition, those two vectors, the vectors that are the initial condition of a given geodesic. Now our next step is just to expand this any given geodesic in a Taylor series. This Taylor series stuff is really huge for the work we're doing. So we need to expand this function, which represents a given geodesic, given these initial conditions, in terms of its Taylor expansion around the point tau equals 0. And now the Taylor expansion is actually kind of easy because this is a function of one variable, right? This is like elementary calculus Taylor expansion. You just have the 0th order term. The first order term is just tau times the first derivative. The second order term is tau squared times the second derivative. The reason you don't have all of these x minus xp's is because we're doing this around the point 0, right? So this is all, so tau is x minus x0. I guess this is what I think it was called the Maclaurin series in elementary calculus, right? This is about as simple as it gets. So the good news, though, is that we know our initial conditions by assumption, and the geodesic equation gives us this term. So now I can fill in this and this with things that we know, right? This is all the initial things, the initial conditions, and this is the connection in the arbitrary coordinate system. So I can write all this down. And voila, to second order, this substitutes directly for this our initial condition, the tangent, the tangent vector to the geodesic curve at the point P. This x alpha of 0, well, that's the first of the conditions, so that takes care of the 0th order term. And then this guy here, the substitution comes directly from the geodesic equation, which gives us this. And this is known because it is the connection on the spacetime, and we assume that we know what the spacetime is. Remember, we're not solving for any spacetimes here. We assume we know what the spacetime is. This is all just about coordinate transformations, right? But this now is not a coordinate transformation, of course, like it was previously when we did this, right? Back here, when we did our Taylor expansion, we were transforming from one coordinate system, x, to another coordinate system, psi, and it was it was multivariable. It was 4 variables, which is why you've got all these weird sums and multiple partial derivatives. Here, we're just taking a curve, a single curve in the x-coordinate system, which was known to be established, and we presumably know the space-time, so we know the connection. So all this is known. Everything is known. And I guess, by the way, just to add a little focus on this guy, when I write x dot alpha of 0 equals v alpha at the point P, that's my initial conditions, this is a vector, right? So if I were to include this is the components of a vector. So if I was to make it a real vector, I would be putting this partial alpha there because this is clearly intended to be a vector in the coordinate basis because I've given it this index. When I give it this index, I'm tying the vector to the coordinate system, which I'm also calling the x-coordinate system by an abusive notation because I'm calling it the geodesic, but it's also in the x-coordinate system. So, so this is the basis written in the coordinate basis. This is the components of this initial tangent vector to the geodesic in the coordinate basis. And now is when the magic happens and we connect this to this. right, so now we'll refresh our screen here, right? I've written the same expressions up here. I just copied them over. And here is our full vector form of this our initial condition tangent vector to the point. Maybe I should draw, here we have our point P, and through our point P is this geodesic, and at the point P is this tangent vector, and that is given by VP alpha partial alpha in the x coordinate system. But of course, this also equals lambda P A in some arbitrary basis that we set up at the point P, right? I could take any basis for the tangent space TP, any basis at all, and I can still express this vector in terms of that arbitrary other basis, which I'll call E. And in fact, this is a good time to put a little arrow above these to show that these represent the actual little basis vectors, and these guys represent the components with respect to these basis vectors. But this equality still holds because it's the same vector, right? What binds this stuff together is that these vectors can be expressed in terms of those vectors, right? I can write EA alpha, right? EA alpha partial alpha, right? I can say the vector EA equals these components, EA alpha, the basis vector partial alpha, right? That oops, I'm missing an A there, right? So that says how this basis is expressed in terms of that basis. So I can take this and go one step further, and I can write this as lambda P alpha EA alpha partial alpha. And now everything is in the same basis system, right? This is in the same basis system as that, right? So I've now, what that means is that V alpha P equals lambda P alpha E A alpha, right? This is the components have to be the same because I'm in the same basis system now, right? I've used the conversion. I've used our expression of how this arbitrary basis at the tangent space is related to the coordinate basis, and that relationship is just this matrix here. So that's pretty easy. So this expression is solid. But as it stands, it's just a bunch of arbitrariness, right? Because I've got an arbitrary coordinate system which establishes these initial conditions, right? This guy is set in an arbitrary coordinate system, and ergo these coordinate basis is arbitrary. And then at the point in the tangent space, at the point P in that tangent space, I set up another basis system which is arbitrary, and the relationship between the two is pretty straightforward, right? It's pretty clear what it's not hard to see that there would be, I've basically got a relationship between two arbitrary coordinate systems, right? So the difference is that if we assume that the coordinate system on the space-time, this x coordinate system, we've already kind of set that in stone, and I could really play around with the basis system at TP, meaning that the coordinate system x is fixed the coordinate basis in the tangent space at P. But I can play around with this guy as much as I want. Well, what am I going to do? Well, I'm going to set it up so that the basis vectors of this tangent space, my new basis vectors, are going to be orthonormal, which means that G alpha beta of E A alpha E A, or I guess I should say E B beta, right? This is an alpha. What a mess. Right? That has got to be orthonormal, which means it has to equal eta A, B, right? I'm going to insist that they're orthonormal. I'm going to choose them so that this is true. So what was before an assumption, where was that? Given to us by the Einstein Equivalence Principle, right? Where I'm saying this is always true because of the Einstein Equivalence Principle. Now I'm sort of looking at it in terms of it's a choice I'm making of the basis on the tangent space. I can choose any basis in that tangent space I want. So I'm going to choose one whose basis vectors are orthonormal with respect to the Minkowski metric, right? So I make that choice. And so now I know two things. I know this is true, right? And then once I know this is true, it picks out basis vectors that are orthonormal. And once I know that, and I know these basis vectors here, I can now express the initial condition vector in terms of components in the new basis, which are given by these lambdas. Now we make our substitutions into this guy right here. Let me move this up to right there and put that expression back. And we're going to start our substitutions systematically. So we're going to substitute first for this guy. We're going to use this expression here. So I will write x alpha of p plus tau times lambda alpha at p e alpha a. Then I have minus, and I want to put in two factors of that here, right? Beta and gamma. So that, I guess, would have to look like, wait a minute. If I look at this, this is not right? I'm not summing correctly here. So I will fix that to be what it's supposed to be, which is an A, right? And I think these are all right. I got beta, gamma, beta B, gamma C. Hold on, that's not right. This has to be, this has to be a small b, Latin B, and a small Latin C, right? So this is B and C, like that. So these are summing up, and all that's left is these sum out, and you're left with just one alpha at the top. That sums, that sums, that sums, and that sums, right? And this is now our substitution, right? These guys are, again, fixed by this process. This is known from the space-time, and these guys are known because you pick your initial vector conditions. So your initial vector selects lambda in this basis, or in the basis, our new orthonormal basis of the tangent space at P, and you end up with this expression for the geodesic. So this is where, from the last lecture, you remember what we did was or from a previous lecture on the subject, right, one or two lectures ago, we were saying if you have your point P and you have an arbitrary point out there Q, you pick a geodesic that goes through P and Q, and you take that tangent vector that does it, and you tune the tangent vector to the right length so that just one unit of traversal, meaning tau equals 1, gets you from P to Q exactly, and then you take the components of that vector and you call that the coordinates, right? So now that we have this Taylor expansion, we can interpret it as a coordinate transformation. Instead of a Taylor expansion along a geodesic, we're going to interpret it as a coordinate transformation. So you may remember in our just a little while ago, this was the coordinate transformation we came up with, right? And look, it's got the same guys are here. I intentionally chose the same symbols, but obviously these are going to be shown to be the same, right? But this would be a coordinate change from an arbitrary coordinate system X to this inertial at P system. But you can invert this, right? You can invert this because it goes both ways, and you can write this same coordinate transformation from the to figure out the arbitrary coordinates knowing the inertial at p coordinates. And how would that look? Let me write it down. So this is the inverted form, right? This is exactly, just the opposite of this, but now it's just x for E alpha. But notice you still retain the connection coefficient in the known system, right? Because you got to have everything known on this side. Remember, this is a function for these coordinates, for the new coordinates via the old coordinates. Well, the old coordinates are the only input. So these things here are your only inputs. Everything else has to be known, right? So this is known from the original geometry. These are known because of the, when we derive this, these are known because of the Einstein Equivalence Principle says they exist, and then this is assumed to be known. So this is the only inputs here. But this guy now looks an awful lot like that guy if we start lining things up correctly. For example, this part right here is literally found up here, right? So that's the same. This piece, and likewise this part right here, is literally found in the equation. So those parts are just one-to-one correspondence. The part that we have to understand is the part that reflects the coordinates, right? This is, you assume that the coordinates of P in this inertial at P system is given by this. Let's not assume it's 0, right? Let's assume it's some number. This is that distance in coordinate distance away from the coordinates of the point P. Well, that piece carries an index A because there's 4 of those differences. There's 4 coordinates, so there's 4 coordinate differences. So that piece carries an A. Well, this is what carries an A here, right? So this part right here is all that we can do to correspond to that. So we have to write tau lambda P A for that part, right? And you'll notice over here, we have 2 of them, right? We have a tau squared, and then we have 2 of these perfectly to correspond to those 2. So this one will be tau lambda P B and tau lambda P C. Ergo, now what we have is this geodesic equation, ultimately, the second order form of the geodesic equation, has exactly the same structure as a coordinate transformation if the coordinate difference is given by this expression here, right? So now if we use our initial condition that EP equals 0, EP mu equals 0, that is the origin of the inertial coordinate system at the point P is just established to be 0, which was an initial condition that we were operating under. Oh, I think that's the previous slide. Hold on. That was it this slide? Yeah, this slide here, right? This initial condition right here was that x of 0 is xp. Well, I guess we never really applied this initial condition, right? The point is that when tau is 0, when the parameter is 0, you're at the point P. That's what this condition says. We can furthermore go and say that that coordinate is 0. And so that these guys are just 0, right? The whole goal is to say that 0, and that 0. And ultimately now, the coordinate in the inertial system is given by these numbers right here, right? And those are linear, right? They're linear, right? They're linear in the parameter tau. They're along geodesics. They're along geodesic paths. And ultimately, that's sort of the whole point. That is the Riemann Normal Coordinate System, where the magnitude, right? Remember, these are vector components, right? These were the vector components of this initial vector, right? Did I write that down here somewhere? Yeah. But these are vector components in this tetrad system, right? This tetrad system. We force the tetrad to be nice and orthonormal. So that's a way of asserting that we're choosing a specific one. So we have these nice orthonormal tetrads. So we're now projecting this initial basis, this initial tangent vector in terms of this orthonormal tetrad. These are the components of the orthonormal tetrad. And down here, those components show up as though they were coordinates in a coordinate transformation. And that's what Riemann normal coordinates are. Now, the last step in the previous time we developed this, when we first talked about Riemann normal coordinates, this tau is an arbitrary free-floating factor. So what we do is, remember I said we tuned the tangent vector. Do I still have that drawing yet? Remember I said we tune this tangent vector's length so that you arrive at the point Q, at the point that you're trying to characterize in this coordinate system, so that tau equals 1. Well, the way we assert that formally is down here. We just say, okay, tau is going to always equal 1. That means but we can compensate for that 1 by just changing the length of the initial vector, the length of VB, so that that all of this coordinate now simply exists entirely in this definition. In other words, lambda absorbs the tau, and lambda literally becomes the coordinate in these Riemann normal coordinates. Ergo, there it is. So that's, we've now proven, right? We've now proven and constructed, using the Einstein Equivalence Principle and the notion of these geodesics, geodesics flowing through a certain point. We've connected those two together to show that we can create this Riemann normal coordinate system. And by the way, it'll always be nice and orthonormal, right? Meaning it's going to also be inertial. So this geodesic coordinate system is very, very well adapted to being this inertial coordinate system at a point P. Okay, so in the next lecture, we're going to apply this. We're going to apply the Riemann normal coordinate system, and we're going to learn how to calculate different things like the curvature tensor inside when you have Riemann normal coordinates. Expanding, we're going to expand the metric in a Taylor series using Riemann normal coordinates. The key takeaway is that the Einstein Equivalence Principle always says that we can always establish this coordinate system. For sure, we can always establish a coordinate system like this. Now, it's not unique, but Riemann normal coordinates is one of the coordinate systems that the Einstein Equivalence Principle demands exists, right? And in addition to that, we can always build it, right? At any given point, we can erect this Riemann normal coordinate system. So we're basically, the RNC is just a way of taking the EEP and establishing a real exemplar of it. And it's a tool. So we can always say now, go to a point and set up Riemann normal coordinates. And once I do that, I don't have to literally tell you exactly how to do it because I'm speaking in the abstract, right? Part of it, if I'm going to establish a tetrad basis there, I still need to know geodesics. I need to know the curvature of spacetime. I need to know the metric on the spacetime in some coordinate system, all the transformations. We can still speak hypothetically, but I can always assert that at every place I can do this procedure, establish Riemann normal coordinates. You know that these things are true in those coordinates. You know geodesics are straight lines in those coordinates, locally to the point. And from there, you can now study general relativity inside that coordinate system, and we're going to discover some nice simplifications that we're going to take advantage of. And ultimately, the whole point of this, the reason we're going down this rabbit hole, is that we want to study an interpretation of the curvature scalar, which takes advantage of Riemann normal coordinates as a tool. Okay, so the next lesson we're actually going to begin